Hello and welcome. In this video, we will be exploring the fundamentals of vectors in 2 dimensions, a key topic in the IB Mathematics Analysis and Approaches higher level curriculum. By the end of this session, you will be able to: first, define and represent vectors in both component and unit vector form. Second, understand and apply the concept of vector equality. And third, calculate the magnitude of a vector and identify unit vectors. These concepts are foundational for more advanced vector operations and applications, so a solid understanding is essential. Let's begin by defining what a vector is. In the Cartesian plane, we can plot a point, say P, with coordinates 2, 5. To get to this point from the origin, we move 2 units in the x direction and 5 units in the y direction. A vector is a quantity that has both magnitude, or size, and direction. We can represent the movement from the origin O to the point P as a vector. This vector, written as OP, can be expressed in component form as a column matrix, 2, 5. The top number is the x component, and the bottom is the y component. This is called the position vector of point P, as it describes the position of P relative to the origin. We can also express this vector using unit vectors. We define I as the unit vector in the positive x direction, which is 1, 0, and j as the unit vector in the positive y direction, which is 0, 1. The term unit vector means it has a length of 1 unit. We'll discuss magnitude in more detail later. Using these unit vectors, we can write the vector OP as 2i plus 5j. This is called the unit vector form. So the component form, 2, 5, and the unit vector form, 2i plus 5j, are 2 different ways to represent the exact same vector. To recap, we've seen that a vector can be written in component form as a column matrix or in unit vector form using I and j. Both forms represent a quantity with magnitude and direction. Now, let's consider the concept of vector equality. This is a fundamental principle in vector algebra. 2 vectors are equal if and only if their corresponding components are equal. This means their x components must be the same and their y components must be the same. Let's look at an example. Consider the vectors OA and CB shown on this grid. Vector OA starts at the origin, 0, 0, and ends at point A, 3, 1. To find its component form, we subtract the starting coordinates from the ending coordinates. So OA is 3 minus 0, 1 minus 0, which is 3, 1. Now let's find vector CB. It starts at C, minus 1, 2, and ends at B, 2, 3. Its component form is 2 minus minus 1, 3 minus 2, which simplifies to 3, 1. Notice that both vectors have the same component form, 3, 1. This means they are equal. In unit vector form, both are 3i plus j. This equality is visually represented by the fact that the arrows are parallel and have the same length. They represent the same displacement, just starting from different points. So, to reiterate, 2 vectors are equal if their components are identical. This implies they have the same magnitude and the same direction. Let's apply this concept of vector equality to solve for unknown values. This is a common type of problem in the IB exam. Consider the equation. The vector a plus 1, 2b minus 8 is equal to the vector 9 minus a, comma a. Our goal is to find the values of a and b. Using the principle of vector equality, we know that the corresponding components must be equal. This gives us a system of 2 equations. First, we equate the x components. A plus 1 equals 9 minus a. Second, we equate the y components. 2b minus 8 equals a. Now we can solve this system. Let's start with the first equation, as it only involves a. Adding a to both sides gives 2a plus 1 equals 9. Subtracting 1 from both sides gives 2a equals 8. Dividing by 2, we find that a equals 4. Now that we have the value of a, we can substitute it into the second equation to find b. Substituting a equals 4 into 2b minus 8 equals a, we get 2b minus 8 equals 4. Adding 8 to both sides gives 2b equals 12. Dividing by 2, we find that b equals 6. So, by applying the rule of vector equality, we have found that a equals 4 and b equals 6. This demonstrates how a vector equation can be broken down into a system of scalar equations. Next, let's discuss the magnitude of a vector. The magnitude is simply the length of the vector. For a vector A with components a1, a2, its magnitude, denoted by A, can be found using the Pythagorean theorem. Imagine the vector as the hypotenuse of a right-angled triangle. The horizontal side has length 1, and the vertical side has length 2. By Pythagoras, the square of the hypotenuse is the sum of the squares of the other two sides. So the magnitude squared is a 1 squared plus a 2 squared. Taking the square root, we get the formula for the magnitude. The square root of a 1 squared plus a 2 squared. Let's work through an example. Suppose we have the vector p equals 3 minus 5. To find its magnitude, we apply the formula. It's the square root of 3 squared plus negative 5 squared. This is the square root of 9 plus 25, which equals the square root of 34. The magnitude is the square root of 34 units. Now let's consider another vector, q equals 2i minus 5j. First, we convert it to component form, which is 2 minus 5. Then we find its magnitude using the formula. It's the square root of 2 squared plus negative 5 squared. This is the square root of 4 plus 25, which equals the square root of 29. The magnitude is the square root of 29 units. So, to find the magnitude of any 2D vector, you square its components, add them together, and then take the square root. This gives you the length of the vector. A special type of vector is a unit vector. As we mentioned earlier, a unit vector is any vector that has a magnitude of 1 unit. The base unit vectors I and j are examples of unit vectors. The magnitude of I is the square root of 1 squared plus 0 squared, which is 1. Similarly, the magnitude of j is 1. Let's work through a problem to find an unknown component of a unit vector. Suppose we are given that the vector minus 1/3 k is a unit vector. We need to find the possible values of k. Since it's a unit vector, its magnitude must be equal to 1. We can set up an equation using the magnitude formula. The magnitude is the square root of negative 1/3 squared plus k squared. We set this equal to 1. To solve for k, we can square both sides of the equation. Squaring both sides removes the square root. Negative 1/3 squared is 1/9. So we have 1/9 plus k squared equals 1. Now we isolate k squared. Subtracting 1/9 from both sides gives k squared equals 1 minus 1/9, which is 8/9. Finally, we take the square root of both sides to find k. Remember to include both the positive and negative roots. The square root of 8 is 2 times the square root of 2, and the square root of 9 is 3. So k equals plus or minus 2 root 2 over 3. This means there are two possible vectors that satisfy the condition of being a unit vector with an x component of negative 1/3. Both have a magnitude of 1. Let's now tackle some problems involving geometric figures, which are very common in the IB curriculum. We'll use the concepts we've learned to find vector expressions. First, consider a square ABCD. We are given that the vector AB is P and the vector BC is Q. We need to find expressions for CD, AC, AM, and BM, where M is the intersection of the diagonals. Let's start with CD. In a square, opposite sides are parallel and equal in length. This means they represent the same vector. Therefore, the vector CD is equal to the vector BA. The vector BA is the negative of AB, so CD equals negative P. Next, let's find AC. We can think of moving from A to C as moving from A to B, and then from B to C. This is vector addition. AC equals AB plus BC, which is P plus Q. Now for AM. The diagonals of a square bisect each other. This means M is the midpoint of AC. So the vector AM is half the vector AC. Substituting our expression for AC, we get AM equals 1/2 of P plus Q. Finally, let's find BM. We can move from B to M by going from B to A, and then from A to M. So BM equals BA plus AM. We know BA is negative P, and we just found AM. Substituting these in, we get BM equals negative P plus 1/2 of P plus Q. We can simplify this expression. Distributing the 1/2 gives negative P plus 1/2 P plus 1/2 Q. Combining the P terms, we get negative 1/2 P plus 1/2 Q. This can be factored to 1/2 of Q minus P. This problem demonstrates how to use vector addition, subtraction, and scalar multiplication to navigate a geometric figure. Let's try another geometric problem, this time involving a regular hexagon. We have a regular hexagon, PQR-STU. The vector PQ is A, and the vector QR is B. The diagonals intersect at the center, X. We need to find expressions for PX, PS, QX, and RS. First, let's find PX. In a regular hexagon, the vector from a vertex to the center is the sum of the two adjacent side vectors. So PX equals PQ plus QR, which is simply A plus B. Next, let's find PS. The vector PS is a diagonal that passes through the center X. This means PS is twice the vector PX. So PS equals 2 times PX, which is 2 times A plus B. Now for QX. We can find QX by going from Q to P, and then from P to X. QX equals QP plus PX. QP is the negative of PQ, so it's negative A. We already found PX is A plus B. Adding them together, we get negative A plus B, which simplifies to B. Finally, let's find RS. In a regular hexagon, opposite sides are parallel and equal in length. This means they represent the same vector. The vector RS is equal to the vector QP. As we just saw, QP is the negative of PQ, so RS equals negative A. This problem highlights the symmetry of a regular hexagon and how it simplifies vector calculations. Let's conclude with a problem that combines vector addition, scalar multiplication, and the concept of parallel vectors. In this figure, the line segment BD is parallel to OA, and its length is half the length of OA. We are given that OA is vector A, and OB is vectored B. We need to find expressions for BD, AB, BA, OD, AD, and DA. Let's start with BD. Since BD is parallel to OA and half its length, the vector BD is half the vector OA. So BD equals 1/2 of A. Next, let's find AB. We can go from A to B by going from A to O, and then from O to B. AB equals AO plus OB. AO is the negative of OA, so it's negative A. Therefore, AB equals negative A plus B, or B minus A. Finding BA is straightforward. It's the negative of AB. So BA equals negative of B minus A, which is A minus B. Now for OD. We can go from O to D by going from O to B, and then from B to D. OD equals OB plus BD. We know OB is B, and BD is 1/2 A. So OD equals B plus 1/2 A. Let's find AD. We can go from A to D by going from A to O, and then from O to D. AD equals AO plus OD. AO is negative A, and OD is B plus 1/2 A. Adding them, we get negative A plus B plus 1/2 A, which simplifies to B minus 1/2 A. Finally, DA is the negative of AD. So DA equals negative of B minus 1/2 A, which is 1/2 A minus B. This problem demonstrates how to use given information about parallel lines and lengths to build up complex vector expressions from simpler ones. Let's recap what we've covered today. We started by defining vectors as quantities with magnitude and direction, and learned to represent them in component form x, y and unit vector form xi plus yj. We then established the principle of vector equality, stating that two vectors are equal if and only if their corresponding components are equal. This allowed us to solve for unknowns. Finally, we learned how to calculate the magnitude or length of a vector using the Pythagorean theorem, and we defined a unit vector as any vector with a magnitude of 1. These concepts are the building blocks for all of vector geometry and will be crucial as you progress in your IB studies. You are now able to define and represent vectors, apply vector equality, and calculate vector magnitudes. To solidify your understanding, here are 5 practice questions in the style of the IB exam. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Find the values of p and q if the vector 2p minus 1, 3q plus 2 is equal to the vector p plus 3, q minus 4. Question 2. Given the points a1, 5, b4, 1, and c2, 7, find the vector ab in component form and its magnitude. Question 3. The vector v equals 3i minus 4j. Find the unit vector in the same direction as v. Question 4. In a parallelogram OABC, OA is vector A and OC is vector C. The diagonals intersect at M. Find the vector OM in terms of A and C. Question 5. A vector has a magnitude of 10 and its y component is 6. Find the possible x components of the vector. Welcome back. Let's go through the solutions to the practice questions. For question 1, we equate the components. 2p minus 1 equals p plus 3, which gives p equals 4, and 3q plus 2 equals q minus 4, which gives 2q equals negative 6, so q equals negative 3. For question 2, vector AB is 4 minus 1, 1 minus 5, which is 3 minus 4. Its magnitude is the square root of 3 squared plus negative 4 squared, which is the square root of 25, or 5. For question 3, the magnitude of v is the square root of 3 squared plus negative 4 squared, which is 5. The unit vector is v divided by its magnitude, so it's 1/5 of 3i minus 4j, or 3/5 I minus 4/5 j. For question 4, in a parallelogram the diagonals bisect each other, so OM is half of the diagonal OB. OB is the sum of OA and OC, which is A plus circa. Therefore, OM is 1/2 of A plus C. For question 5, let the vector be x, 6. Its magnitude is the square root of x squared plus 6 squared, which is 10. Squaring both sides gives x squared plus 36 equals 100. So, x squared equals 64, and x equals plus or minus 8. I hope these solutions were helpful. Keep practicing these fundamental concepts, as they are essential for success in IB Mathematics AAHL. Thank you for watching.